Okay, so welcome to this live session on 01/07/2026. Okay, so this today we'll be discussing week 3 content. Okay, so basically in week 3, the major topics covered are transfer function and based upon the transfer function, stability, and also the block diagrams. Okay, so previous week, if you see week 2, so basically week 2 has majorly on the uh, Laplace transforms, correct? Okay, Laplace transforms. Okay, so where in Laplace transform, I think Madam has explained the definition of Laplace transforms. So the for various standard signals, okay, the Laplace transforms. Okay, then uh, properties of Laplace transforms. So then inverse Laplace transforms, correct? Then application of Laplace transforms to ODEs, correct? So these are the major topics covered in the week 2. Okay. Now we are slightly shifting to the four concepts of uh, control systems. Okay, in week 3. So mostly we will use these Laplace transforms which are covered in week 2 in week 3. Okay, so if you go back and see the previous example, okay, so the series RLC circuit example I have explained uh, in week 1. Okay, so let us consider series RLC circuit. Okay, so let's say we have this V of t. Okay, so we have R, L, and C. Okay, so and C, this is the current I of t. Okay, so what is the equation if you apply the KVL in this loop? Okay, so write KVL equation. Okay, write KVL equation. What do we get? Minus V of t plus Ri of t plus L di of t by dt plus 1 by C integral minus infinity to t I of t dt equal to 0. Am I correct? Okay, so if you take the uh, if you differentiate the entire equation, okay, what do we get? So we'll get it like dv of t by dt equal to r di of t by dt plus l d square I of t by dt square plus 1 by c multiplied I of t. Am I correct? So this, if we put it in the order, okay, so dv of t by dt equal to L d square I of t by dt square plus R di of t by dt plus 1 by C I of t. Correct? Suppose in this circuit, if you assume this is the input you are giving and this is the current is the output. Okay. So what do you see? We have separated input terms and output terms. Okay, basically this is differential equation, ODE. Okay, so we have separated input terms here and we have separated all output terms. Okay, so basically this is so ODE. Am I correct? So here you may consider this is a system. Okay, you may consider this is a system Okay. So the system you are giving something called as the input and you are getting the output. Correct? So basically here, this is the electrical system. Correct? So is there any questions? Are there any questions on this? So now I'm trying to generalizing it. Okay, whenever you have some system, it could be electrical or it could be mechanical or it could be something else. So this system would have uh, input and output. Okay, so if we write down the equations, in this case they are electrical equations. So KVL equations. If it is a mechanical system, we write kinematic or dynamic equations. So finally, we will end up with what? We will end up with an ODE. Okay. So is this clear? Any queries? Okay. So now,
Yes, sir.
yeah. So now, so since we are saying that a system, so in general, a system input and output. Okay. So let's say input is U and output is Y. Okay. So now let us consider, okay. So nth order, nth order LTI dynamic system. Okay, so basically we call these systems are dynamical systems. We have already seen those definitions. So what is LTI? Linear time invariant. Okay, linear time invariant. Okay, so in the first class, we have already seen some problems on how to define the linearity and examples and time invariant systems also. So in general, nth order system can be defined as, if you model the equations, it could be like this. So a naught y plus a1 dy by dt plus a2 d square y by dt square plus etc. plus an. Okay. So an dn y by dtn. Okay. Left side. Right side is similar way. B naught u plus b1 du by dt plus b2 d square u by dt square plus etc. plus, so the ending term could be bm. Okay. So dm u by dtm. Okay. Now you see this. Once we write the modeling equation for this modeling, okay, so we get this equation. Okay, for that system considering input u and output y, if we write the modeling equations, so modeling in the sense applying KVL in this electrical circuit. If it is a mechanical system, apply the Newton's laws, etc. Okay, so we get this general differential equation. Okay, any queries? Okay, so now in this equation, okay, let us consider okay, all initial conditions are zeros. All initial conditions are zero. Okay, so this is very important point. What is the meaning of all initial conditions are zeros? Okay, all initial conditions in the sense, okay, so the input terms and output to input and output at t is equal to zero, all they are zeros. Okay, for example, inputs u of zero is zero. It's all its derivatives, etc. They're all zeros. Okay, similarly, output also y of zero, y dash of zero, y double dash of zero, etc. equal to zero. Is this clear? So we are considering this assumption. Okay, all inputs and outputs at initial state, they are zeros. Initial time, we say that all initial conditions are zeros. Okay, now, so let us consider this equation is the equation one. Okay, so now in previous live, we have already seen the Laplace transform when we apply to the differential equation. Okay, so let us say in general dy by dt. So what is the formula? The formula is like, yes, y of s minus y of 0. Correct? So similarly, we could write Laplace transform of d square y by dt square. Okay, so can anyone tell me what is this? S square y of s minus s y of 0 minus y dash of 0. Am I correct? So in general, we could do write the Laplace transform of dny by dt square. Okay. So now consider this differential equation. Okay. So consider this entire differential equation. Okay. So apply the Laplace transform. Okay. So apply the Laplace transform on both these sides. Okay. So when you apply individually, what do you get? A naught y of s plus a1. So what is this one? Is going to be, okay, sy of s minus y of 0. Correct? Similarly, the next one, a2 s square y of s minus s y of 0. This should be small. Okay, minus y dash of 0. Am I correct? So and so on. Okay, similarly, the b naught u of s plus b1 s y of s minus u of 0. Okay, this should be u. Okay, so plus b2 s square u of s. Okay, minus s u of 0 minus u dash of 0. Correct, etc. Correct. So now we already have, we took the assumption that all initial conditions are zeros. Okay, so when you take all initial conditions 0, okay, so now I can write this one like, so all initial conditions are zeros. Okay, so now I can write it like, after removing all the initial conditions. Okay, so you can see, uh, I'll take y of s common. Once all the initial conditions are zeros, I can take y of s common from the left side. I can take u of s common from the right side. Okay, then I can write this ratio. Okay, b naught plus b1 s plus b2 s square etc plus bm s power m divided by a naught plus a1 s plus a2 s square plus etc plus an s power n. Is this clear? Any doubt here? Okay. So now if you see this expression as numerator polynomial. Okay. So numerator polynomial is n of s. The denominator polynomial is d of s. Okay. So let me copy this. Okay. So now what I'll do is, okay, so from the numerator, I take bm out. Okay. So in the denominator, I'll take a1 out, an out. So I'm just taking common. Okay. So what do I get here? Sm. Write it in the reverse way. So bm minus 1 by bm, sm minus 1. So etc. What is the ending term? What is the ending term? 1 by bm, b naught. Am I correct? Similarly, here also s power n. Okay. This will be an minus 1 by an, s power n minus 1, etc. What is the last term? 1 by an, a naught. Okay. So I'll write this term as some k. because they both are constants. Okay, I'll write that term as some k. So now I'll write this one as k multiplied, okay, s power m plus b m minus 1 bar. So this ratio s power m minus 1 etc plus b, uh, the last one is bm. Okay, so that will be like what we can write, b1 bar s plus b naught bar. Okay, similarly I can write it like s power n plus bn minus 1 bar, s power n minus 1 etc plus this will be a. Okay, so a1 bar s plus a naught bar. Is it clear? Any queries? Okay, so here assume that, so m is less than or equal to n. M is less than or equal to n. Okay, so it means that numerator polynomial is less than the denominator polynomial. Okay, so now I can write this one as something like, okay, I can divide this into the roots. This also I can divide into roots. Okay, so I can divide the roots as, let's say, s minus z1, s minus z2. So how many roots I'm going to get? S minus zm. Okay, the numerator polynomial. The denominator polynomial is s minus p1, s minus p2. Okay, so etc. So s minus pm, pn. Okay, so now you can see here. So let me copy it again, this part. Okay, so this is nothing but y of s by u of s. Okay, so this is numerator and this is denominator. Okay, so now in this, if you see, okay, so suppose how are we going to get z1, z2, etc.? If you take the numerator and make it equal to 0, okay, the roots are nothing but, okay, the roots are nothing but z1, z2, etc., zm, correct? And if you take the denominator and make it equal to 0, in this case, the roots are nothing but p1, p2, etc., pn, correct? Now suppose in this, suppose in place of s in the numerator, if I substitute s is equal to z1, what will happen to the entire equation? I don't touch the denominator, just in the numerator. If I substitute s is equal to z1, what will happen?
It will become 0.
It will be 0, correct? So that's why we call these numerator roots are zeros. Okay. Similarly, in the denominator, if I substitute s is equal to p1 or any of these p's, what will happen?
Indeterminate form,
It will be
something
infinity.
by
It
0.
will be infinity, correct? So some constant by 0. Okay. We call them as poles. Okay. What does it mean? So zeros leads the entire, this one output by input makes the 0, and poles they'll make the entire output goes to infinity. Okay, so we also call this particular d of s equal to 0, this equation, as characteristic polynomial. Characteristic polynomial, because in overall control systems the poles will plays very crucial role. Poles will plays very crucial role. Clear? Any doubts? Any
No,
doubts?
sir.
Yeah. And
Sir, here I
yeah,
have one doubt. Like
yes.
in transfer function, like number of zeros is always equal to number of poles, or
No, no, that will
we
come to that
can
point. We'll come to that point. So here
okay, sir.
the uh, g of s equal to y of s by u of s. Okay, where basically this y of s is nothing but what? Laplace transform of output. This is Laplace transform of input, correct? So this is called as the transfer function. This is called as the transfer function. Okay. What is the definition of transfer function? Definition of transfer function is so the Laplace transform of output, the ratio of Laplace transform of output to the Laplace transform of input. Is it ends? Not exactly. Okay. So there is one assumption we took. What is that assumption? The assumption is all initial conditions are zero. Okay. If we don't take initial conditions, we don't get the we don't get the expression like this. Correct? Okay. So the transfer function definition, you must mention that initial conditions are zero. Okay. Any doubt? Okay. So now let us see the example. Okay. We'll consider different functions and try to see what are the poles and the zeros. Okay. So let's say first. So g of s is equal to 1 by s. Okay. It looks like y of s by u of s. Okay. So now tell me how many poles and how many zeros we have.
1 0 1 4.
Yeah. So
There is no zero.
this we can write it like 1 by s minus 0. Correct. So obviously the pole at 0. Correct. We have only one pole. That pole value is 0. Correct. And in the numerator we have no polynomial. So we say that no zeros. No zeros. Okay. So this what we will do is we represent in the S plane. Okay. So basically S plane is nothing but you'll have these uh, two-dimensional axis, two-dimensional plane. You'll have real of S, okay, which we also called as the sigma axis. Okay. So this is imaginary axis on y axis. We also call this as the j omega axis. Okay. Here poles and zeros. Okay. So we represent poles with star mark. So zeros with circle. Okay. So now in this example, what do we have? So we don't have any zeros. We have only one pole that is located at 0. Is this clear? Okay. So that is located at origin. Okay. So this we call it is as a pole zero diagram. Given the transfer function, find its poles and zeros and plot them on the S plane is called as the pole zero diagram. Is this clear? Any doubts? Okay. So now this is the same example. We have g of s is equal to okay, fine. So we have g of s is equal to what? 1 by s. Okay. So basically, you remember the inverse Laplace transform. What is 1 by s is the Laplace transform of what?
Unit step.
Unit step. Okay. So that means I can write it like what is d of t? That will be like u of t. Am I correct? So if you plot it, okay. So this is t, this is d of t. Okay. So the response is always 1. Am I correct? Okay. So what is happening here? The response is always maintaining one. It's neither decreasing or uh, nor increasing. Correct? So this is example, one example. Is there any doubt in this? Any doubt? Okay. Let us see the next example. Okay. Let us say now g of s is some kind of b by s square plus b square. Okay, b by s square plus b square. Okay. So now in this, what are the zeros? Here also no zeros. Correct. What are the poles? Can anyone tell me what are the poles?
plus minus
At
JB.
B minus B.
Plus jb minus jb. Correct. So simply how we are finding this, make numerator equal to 0 and denominator equal to 0. Okay. So now in this case, okay, so can you tell me where should I locate? This is sigma axis, this is j omega axis. Okay. So let us assume b is positive in this case. Okay. So let us assume b is positive. Okay. So where will be uh, plus jb exists? Somewhere here. That will be plus JB. Where will be minus JB exists? Somewhere here. This is pole zero diagram of this transfer function. Okay. So similarly here we have G of S. So can you tell me what is G of T? What is G of T? Sin BT. Am I
Sine B.
correct? Yeah. So because G of S, B by S square plus T square is the Laplace transform of sin BT. Okay. So now if you plot it, so you'll have something like this sinusoidal function. Okay. This is T, this is G of T. Am I correct? So this is pole zero plot, and this is the time domain part plot. Okay. So here again the response is neither decreasing, okay, nor increasing. Okay. It is oscillating. It is oscillating. Okay. So between these two values. Okay. It is bounded. We will say this one is bounded between these two uh, limits. Correct. Now let us consider one more example. Okay, so let us say g of s plus a divided by s plus a whole square plus b square. Okay, so now tell me what are the poles, what are the zeros here, what are the poles? So again consider a is greater than 0, b is greater than 0, some numbers. Okay, what are the zeros? Minus
Minus
a.
A.
So what are the poles? Isn't it like this? A plus jb
Minus A minus JB plus
minus a minus
minus A
jb. Am I
minus
correct?
JB.
Okay. So just plot them on S plane as well as the time domain. Okay. So on S plane, sigma j omega. Okay. So what are the poles? If A is positive, okay. So A is positive. Sorry, A is positive. So minus A will be somewhere here. Correct. Okay. So this will be plus JB. Okay. This will be minus JB. Okay. So where is the poles location? This is minus A plus JB. Okay. This is minus A minus JB. Is that correct? Yes. Okay. Then 0. 0 is at minus A. So 0 is at minus A. So we show this 0 with a circle. So this is the pole 0 plot. Okay. So now if you plot the response, time domain response, okay, so z of t. What is z of t? Can anyone tell me in this case?
E power minus A,
Yes, e power minus
A
at
minus 80
cos bt,
cos bt.
correct? So now, if you plot these two things, okay, how does cos looks like? Cos looks like it starts at this point and it goes like this. Am I correct? It starts at minus 90, sorry, 90 degrees. Okay. Then e power minus at. Okay, it starts at 1. At a time t is equal to 0, the value will be 1. Okay, let us say somewhere here. Okay, so and then it keep reducing, correct? Yes or no? Okay, so now if
Yes, sir.
you multiply these two, if you multiply these two, okay, so what will you get if you multiply these two? So you'll get something like this. Uh, maybe I'll use another. Yeah. So you'll get something like this. Okay, correct? Am I correct? This is green one is your g of t. Am I correct? Now you see here what is happening. So the it is exponentially decreasing sinusoidal. Correct? Exponentially decreasing. At some point it will become zero after a long time. Correct? This is exponentially decreasing sinusoidal. Okay. Now, so what is the conclusion from these three examples? Okay. Given the transfer function, you can make numerator equal to 0 and find the zeros. You can make denominator equal to 0 and find the poles. Okay. Then you can do the pole 0 plot. Correct? Okay. So now let us do it. Let us draw the overall picture. Okay. So what I'll do is so uh, before going to that, okay, let me. Oh, sorry. So before going to this example, okay, so let me define what is stability. Then we can go back to that. Okay, so what is stability? So let us consider this example. Okay, so g of s equal to, let's say, 1 by s plus 1. G of s equal to 1 by s plus 1. Okay, so what is g of t here? What is g of t?
Sin, to the power minus sin.
E power minus c, correct?
Yes.
Okay, so what is the pole 0 plot? What is the pole 0 plot? Okay, so we'll have a
A pole at minus 1.
pole at minus 1. Okay, so this is sigma, this is j omega. So what is the time domain response? T z of t. It starts at 1 and it keeps reducing, correct? So what did you observe from this time domain response? So in the time domain response, there is a guarantee that after a long time, say infinite time, the response goes to 0, correct? Yes or no?
Yes, sir.
Okay, now suppose if I take, let us say this is Z1, okay? Let us say if I take Z2 of S is 1 by S minus 1, okay? What is Z of T in this case?
E to the power t.
E power T, okay? In that case, my pole will be here, plus 1, correct? So what is the response in this case? So
Exponentially increasing.
exponential increase. It also starts at 1, but it increases like this. Am I correct? So this is the Z1 of t, this is the Z2 of t. Okay, when you take pole on the left side, okay, there is a guarantee that your response goes to zero after a long time. There is a guarantee. Okay, particularly when t equal to infinity, in this case here, v of t goes to zero. Okay, but when you take pole on the right side, okay, the response is increasing without any bound. Okay, so now the stability is defined as, okay, stability is defined as, so the behavior of the system, okay, the behavior of the system, okay, so when it uh, when it reach the stable point, when it reach the zero value at the end of the time, after a long time. Okay, this is one kind of stability which we also called as the exponential stability. Okay, so now what is the condition here to make this response goes to zero? What is the condition where my pole should be existed?
Left of the S
left
pole.
hand side.
Exactly. So my pole should be existed on the left hand side. Okay.
So
So
it is
yeah.
here it is final. It should be converges to zero. It is
It's
mandatory, or it may be any other number also, some finite number.
no, no, it has to be converges to zero.
Okay, sir.
Okay, so this is one kind of stability. The other kind of stability what we have is bounded input, bounded output stability, that we'll discuss in the next slide. Okay, so here, so what is the condition for stability? So the pole must be existed on the left side. Okay, if it is existed on the right side, it will be unstable. So let me take one more example. You'll understand much better because here I have considered only one pole. Okay, let us consider multiple poles. Okay, so let us say g of s equal to s plus 2 divided by s plus 3 s minus 1. So here I have both mixed poles. Okay, so now tell me what are zeros here. Zeros is minus 2,
Minus
correct?
2,
What are the poles?
minus
Minus
3 and
3, 1, correct? Okay, now we'll try to find the response using the inverse Laplace transform. Okay, so how do I write this one using partial fractions which you have learned in your plus 1 or plus 2? So a by s plus 3 plus b by s minus 1. We can write it like this, correct? So this will be like s plus 3 s minus 1. Okay, so uh, what do we get? A multiplied s minus 1 plus b multiplied s plus 3. Am I correct? Okay. So if you compare this side, what we have, s plus 2 by s plus 3 s minus 1. Okay. If you compare the like terms, because the denominators are same. Okay. If you compare the s terms on both these sides, compare. Okay. So left side, that means what? Here. This is right side. So left side, what we have, yes, coefficient is 1. Right side is A plus B. Am I correct? Okay. Now, if you compare the constants on both the sides, left side is 2, right side is minus A plus 3B. Am I correct? Okay. So if you solve these equations, you will get A as 1 by 4. Okay. B as 3 by 4. Okay. Now I can write my G of S as, okay, so 1 by 4 by S plus 3 plus 3 by 4 by S minus 1. Am I correct? Okay. Now tell me what is G of T?
1 by 4 e to the power minus 3t
1 by
plus 3
4
by
e
4
power minus 3t
plus 3
plus
by 4
3
e to
by
the
4
power
e power minus t. Sorry, plus t.
plus t.
Okay. So plus t. Okay. So this is what we have now. Okay. So now let us draw pole zero plot using this. Okay. Time domain using this. Okay. So let's draw that pole zero plot. Okay. Sigma j omega. Okay. and time domain plot g of t. Okay. So what are the poles we have? Minus 3, 1. Okay. So minus 3 is this, 1 is this. Am I correct? And 0 at minus 2. Okay. Is this correct? Is this correct? Yes. Okay. Now, so z of t. Okay. Z of t, you have two exponential terms. One will start at 1 by 4. One will start at 1 by 4 and reduces to 0. That is first term. Second one will start at 3 by 4. Okay. So let me take this one here. 1 by 4 and reduces like this. Second will starts at 3 by 4 and increases like this. Correct? Okay. Now, so you have to add both. You have to add both. So if you add both, what will happen? Can anyone tell me? Will it reduces or increases?
It will go to infinity.
Yeah, it never reduces or it never converges to 0. Okay. So maybe it is something like this. Correct? It would never converges to 0. Now see this. So now comment on stability. Can anyone tell me whether this is stable or not?
Not stable.
Not
So we
stable.
have to
Why
consider
it is
the
not stable?
ROC.
It is not converging to 0.
Yes, sir.
Okay. So by looking at the time response, we are saying that it is not converging to 0, hence it is not stable. So now tell me using the pole 0 diagram,
It is the considering ROC, we can take that one
what is
minus,
ROS?
like ROC is greater than minus 3 and less than 1.
No, you don't need to see the ROC. Just look at the pole's location. We have two poles. Okay. So what is your time domain response have? You see that time domain response has one pole here, correct? Another pole here. So the time domain response is in terms of poles location only, correct? Not in zeros, correct? So it means that the stability can be defined with only poles, not with zeros. Okay, now you see out of two poles, one pole is on the right hand side. This is the right hand side of S plane. This is left hand side of S plane. Okay, and this is J omega axis. Is it clear? So it means that if you have n poles, okay, why this is not why this is not converging to 0? Can anyone tell me? What is the reason? Each term is causing for not allowing it to go to 0. Each term
E to the power t.
e power plus t. Okay, that e power plus t is due to what? The pole on the right side.
Right side.
Yes. Okay. If we have a number of poles, n poles, even if one pole is existing on the right hand side, okay, that will make sure that the system will not converge to 0. Correct? Hence, the system becomes unstable. Is that clear? Even n minus 1 poles are on the left side. Okay. So, for the stability, what is the condition now? Tell me. For system being stable, what is the condition?
All poles must be
All
on
poles
the
must be on the left,
left of the yes
must
plane.
be on the LHS plane, left hand side. Okay. We don't talk about zeros. Stability, we only decide using the poles. Is this clear? Any doubt? Okay, this is most important. Okay, next. So we will write overall picture. Let's say we have this j omega axis. Okay, and we have sigma. Okay, so sigma axis. Okay. So let us say one by one. So based upon the pole's location, we'll decide. So now here we have pole at origin. Okay. What is its time response? What is its time response?
Unit step.
The time response will be unit step. Okay. Let us consider different poles. Okay. So origin, okay, negative real axis, positive real axis, okay, on the j omega real axis, okay. So other than these cases, okay, similarly you'll have here also. Okay, are there any other options? Okay, so now this is LHS, left hand side of S plane. This is RHS. So this is the j omega axis. Okay, we said that the system to be stable this side, unstable. Okay, we call in the middle as marginally stable. Marginally stable. Okay, so now let us see. So the first one, okay, so what is its time domain response? Unit step, correct? Yes or no? Okay,
Yes, sir.
so what is the response of this pole
E
is
to
on
the
the left
power.
side? This will be something like this. Am I correct? Exponentially
Yes, sir.
decaying.
E to the power
Okay,
minus 8.
so similarly, what is on this?
E to the power 80.
It starts here and keep increases. Okay, now also, what about these two? So it will be like sinusoidal. Am I correct?
So
Okay. Now, what about these two? Those two will
exponentially
be
decreasing sign.
exponentially decreasing. Okay. Similarly, what about these two?
Exponentially increasing sign.
Exponentially increasing. Is this clear? Any doubts now? Tell me. Okay. So the in responses you can see. So this is the major case. Okay. This is the major case for stability. Okay. Rest all are unstable. Okay. So this case we call it is as a marginally stable. Okay. But for poles, when you see, when you given the transfer function, okay, if you have poles, so if you have n poles, okay, even if one pole is existing on the right hand side, the system becomes unstable. Clear? Any queries? Any queries?
No, sir.
Yeah. So let me solve one example quickly, then we'll close it. Okay. So example. Okay. So let us say circuit example only. We have a source Vi.
Sir, here I have one doubt. Like Bebo
Yes,
stable and
yes.
stability are both are different or same?
Both are different. Both are different.
Okay, sir.
Okay, that will explain it in the next live. Okay, you have this example. So you have Vi and you have V naught. Okay, so Vi of t, V naught of t. Okay, so the values are 1 Henry, 1 Henry, 1 ohm, 1 Henry, and 1 Farad. Okay, so the question is to find the transfer function. So basically, what is the transfer function here? So find what is the transfer function we defined? Okay, so Laplace transform of output divided by Laplace transform of input. Correct? but the given circuit is in the time domain. This is in the time domain. Okay. So we have to convert this time domain circuit into the Laplace domain. Laplace domain. Okay. Clear? So the question is how to do that. Okay. So circuit will not change. Okay. So time domain circuit to Laplace domain circuit. Okay, so the question is how to do that. Okay, so let me. I hope we have this. You got this one already in your signals and systems or network theory course or circuit theory course. Okay, so I'll explain how to do that. Okay, so what we do generally here is to convert from the time domain to the Laplace domain. We convert each element. Okay, in its Laplace domain. Okay, so the resistor is same. Okay. Now let us see the inductor. Okay. What is the inductor voltage? So inductor
LDI by
voltage
dt.
equation is so L di by dt. Okay. If I take the Laplace transform on both these sides, what do I get? V of S L multiplied S I of S minus I of 0. Is this correct?
Yes,
Okay.
sir.
So what is this? Uh, V of S. Okay. So V of S equal to Ls I of S minus L. Let us say I of 0 is some initial current I naught. Okay. So can you see here? What is right? Left side we have voltage. Correct? So basically this is what this represents this. Okay. L some initial current I naught. So the current is I of t and this is V naught. Sorry. V of t. Am I correct? Okay, this equation is applicable for this. Okay. So now you have two things. One is this is time domain and the time domain circuit. Okay. Now you have this Laplace equation, S domain equation. Now what do we have here on the left side? Or voltage. Correct. What do we have in the right side? Right side also must be voltage equivalent term only. Correct. It is something similar like in middle we have equal to. Okay. So what is that? What basically this one indicates? This one indicates this left side sum of some voltages. Okay. Right side sum of some voltages. What is this basically?
A multiplication of current and the
No,
impedance.
no, no. Left
Some
side you
dish.
have all algebraic sum of voltages. Right side you have
Yes, sir.
algebraic sum of voltages. What is this basically? This is
KVL.
KVL definition. Usually what we do, given a mesh or loop, we write KVL equation. Okay. Now a KVL equation is given to us. Okay. Let us write down the circuit itself. So that circuit uh, could be written like this, which satisfies this equation. Okay. So I'll write this one as LS. Okay. L I naught. Okay. So this is the I of S and this is V of S. Can you check whether this circuit is satisfying? If I write KVL for this circuit, will I get this one or not? Yes. Okay. So simply this is time domain. Okay. This is S domain or Laplace domain. Is this clear? Is this clear?
Yes, sir.
So now here we are supposed to find transfer function. Okay. The definition of transfer function says that initial conditions are 0. Okay. So you can make this I naught to 0. Okay, when you make I naught to 0, what do we get? We get this circuit like this. So V of S, I of S, LS. Correct? Yes or no? Okay. So now I'll write this one as yes. Is it correct? Because that is LS. L is 1. Correct? Similarly, this is also yes. So resistor, it will not change anything. 1. Okay. The input will become Vi of S. Okay. So here the capacitor basically you will get if you do the same thing 1 by CS. That will be 1 by S because this value is 1. Okay. Here also you will get yes. Here you will get yes. 1 by S. Is it clear? Any doubts? So I just did this one for only inductor. Okay. You can do for resistor and capacitor also. Okay. Now you have this Laplace domain circuit. You have this Laplace domain circuit. Okay. You can apply whatever you want. You can apply the write down the KCL equations or you can write down the KVL equations. Okay. So if you wanted to write KCL equations, okay. So you may consider this is reference 0 volts. Okay. This will be VI. Okay. This will be V naught because this is V naught of S. And this will be, let us say, some voltage VA. Okay. I hope you can write the equations, correct? So let me write
Okay,
it.
sir.
Yeah, yeah. Let me write it. I don't want to skip it. Okay. So first what I'll do is node A. This is node A. Okay. So at node A, what is the equation? Basically, VA minus VI divided by S, correct? Plus VA minus V naught by 1. Okay. Plus VA divided by S in parallel with 1 by S. Am I correct? That will be equal to 0. Okay. Similarly, at node 0 means this one. Okay. So V naught minus VI divided by S plus V naught minus VA divided by 1 plus V naught minus 0 divided by 1 by S equal to 0. Am I correct? So what you can do is in these two equations, finally, what is our aim? We have to find a transfer function which is nothing but V naught by Vi. Of course, they are V naught of S and Vi of S. All these also. Va of S, V naught of S, Vi of S. Now what you can do is from the first equation, 1, 2, first equation, you can find the expression for Va. Okay. That expression you can substitute here. Okay. The entire equation will be in terms of V naught and Vi only. Correct? Okay. Then you can find what is V naught of S by Vi of S. Okay. Here I'm giving the direct answer. So you do that is as homework. So S square plus 2S plus 2 divided by S power 4 plus 2S cube plus 3S square plus 3S plus 2. Okay, you can do that. You can also find the poles and zeros also. Okay, clear? Any queries?
No, sir.
Okay, so surprise test. Yeah, surprise test. Okay, so you have a spring mass damper system. You have a spring mass damper system. Okay. So that equation is something like this: t square x by dt square plus 2 dx by dt plus 3x equal to 2 u of t. Okay, this equation looks like same the basic differential equation. Here I would say that x is the output, okay, u is the input. Okay, so question is find transfer function, find poles, zeros. Okay, so pole zero diagram, and also comment on the stability. The question is straightforward, right? Okay, so you have 10 minutes. Okay, so as usual, you write the answer on paper, you take photo of that, and please do mail me within 10 minutes.
So zero here.
Okay, all right, thank you.
So,
Yeah,
can we send it after that 8 p.m.? Actually, DSP session is going to be parallel is going to be parallel with this session.
oh, is it? Yeah, it's fine then.
Okay, sir.
Okay, thanks. Yeah, thank you.
Thank you, sir.
Thank you, sir.